Good morning, everyone. Sorry I'm not able to be with y'all today. Tennis has playoffs, so we're over there. I'm going to split today's lesson kind of into two videos. So the first one we'll do here is going to be focused on a type of force problems. And then I want you guys to go into the OnRamps Canvas page and work through a learning catalytics version, but it'll be in a quiz format on Canvas. It'll be in the college side on the lecture Canvas page. I'll show you again how to access that in just a bit. The first video we're looking at today is going to focus on normal forces and rigid surfaces, specifically two types of problems. And I just kind of want to work our way through a couple example problems. Some of these will help you on the quest. Some may not, but they're all good problems and good ways to look at the forces. If I mess up, I am not going to be able to re-record this video, so just please bear with me, and hopefully everything goes okay. There'll be a second video after this over something called an Atwood's machine that I'd like y'all to do after you've done the rigid forces and normal force learning catalytics on Canvas. A reminder, Thursday, I probably will not see you because of the PSAT, so sorry if I miss you for the whole week because of the holiday and PSAT and tennis for me. But you are always welcome to reach out onto me on Remind to come in for lunch with any questions or anything like that. Don't forget that your post lab is due tonight. That'd be tonight being Tuesday. And that next week, when I see y'all next week, is when Quest 4 is going to be due, and we will spend a decent amount of time that day just working on Quest and working our way through those problems. And I'll probably review a few of the things that we might not have been able to get to because I wasn't here today. So the first one we're going to look at, let's switch over to this video, is what's called oftentimes an apparent weight. So occasionally you might see a phrase that's listed as what we call the apparent weight. And apparent weight is just another name for the normal force. And I'll show you a type of problem where that works out. So the normal force and apparent weight are really identical. It just means the same things. Those are synonyms. So for example, here would be a type of problem where an apparent weight shows up. And essentially what's going on is we have our person standing in an elevator. This is our elevator. There's a cable up here. And our elevator could be doing one of three things. It could be moving at a constant speed. It could be accelerating upwards. Maybe it starts at rest and begins moving up, or maybe it's accelerating downwards. Either it starts at rest and begins moving down, or maybe it's traveling up and coming to a stop, right? Whatever's happening here is going to change a little bit our problem. So let's, for this problem, say our man, here, or our person, whoever he is, has a mass of let's just say 100 kilograms. And let's say our person with a mass of 100 kilograms is in an elevator that is accelerating upwards. And let's say the elevator is accelerating upwards at a rate of 2 meters per second squared. And maybe the question asks, what is the apparent weight? And the idea is basically this. If you're in an elevator, you can feel when the elevator begins to move, and you can feel when that elevator comes to a stop. Maybe not. You have jumped in the elevator while it's accelerating. And if you're jumping while it is accelerating upwards, maybe right when it begins, you might find that you're not able to jump very high. The elevator accelerates upward and it kind of runs into your feet before you make the top of that jump. But if it comes to a stop at that highest point, you might find yourself being able to jump a little bit higher than you normally would have. I wouldn't recommend that because you don't want to accidentally, break an elevator and then get stuck inside of one. But perhaps you've done that or at least imagined doing it. So here's our problem. Our person has a mass of 100 kilograms. The elevator is accelerating upwards. And our question is, what is the apparent weight that this person is experiencing, which is really just saying, what's the normal force? So anytime we're doing a force problem, the first step is always to draw a free body diagram. So here's our free body diagram. And in this free body diagram, I am not looking at the elevator. So I do not need to worry about the tension in this cord. We are just looking at the forces that are acting on our person here. And so what forces are acting on our person? There are only two. The person, of course, has a weight. So the force of gravity, or the weight, is directed downwards as always. And then, of course, there is a normal force directed upwards. And before we go further in the problem, you may note if we have an upward, a positive acceleration, what that must mean, according to Newton's laws, is we also have an upward net force. And if these are our two forces, there should be no big surprise that we should have a larger normal force than the weight. The upward force must be bigger than the weight. Or in other words, if you're in the elevator and it suddenly starts moving upwards, you're going to be pressed into the floor a little bit more than you otherwise would have, because you were at rest and you were wanting to remain at rest, but the elevator begins to accelerate upwards. So how does that look in our equation? Well, our general equation for all of these problems is that net force equals m times a. And so the way we build our problems is our net force just means sum of the forces. So we have a vertical and a horizontal net force, upward forces minus downward forces for the vertical, rightward forces minus leftward forces for the horizontal. And then we say it equals m times a. And if it's at rest or moving at a constant speed, we could also say it equals 0 because it would have 0 acceleration. So for this problem, we have only vertical forces. And so the net force piece of that equation would just be normal minus weight. And remember, I could write it as Fg, but weight is mass times gravity is how we would calculate that. Equals, and then here's where we do m times a. And we have to first say, is it accelerating? Well, if the elevator was moving at a constant speed, the acceleration would be 0, and we would say the normal and the weight here are in fact equal to each other. But that's not the case. Our elevator is accelerating. Therefore, our person is also accelerating. So normal minus mg, upward forces minus down, equals m times a. So if I wanted to find what my normal force was, what would that normal force be? We would just move the weight to the other side, and we find ma plus mg, or the normal force is equal to 100 times 2, which is 200, right? That's mass times acceleration, plus the weight of our person, which is 100 times 9.8, which is what g is. So 200 plus 98, or sorry, plus 980. And so when we add those together, we can, of course, finish out the math, right? 200 plus 980 gives me a normal force in this instance of 1180 newtons. So is the person feeling like they weigh more? Yes. Without the elevator accelerating, they only actually weigh, mg is just 980. But because there's an acceleration, we also have this extra m times a factor. So the person feels like they actually weigh 1180 newtons, more than they normally would have. If this m times a was negative, meaning instead the elevator was accelerating downwards, so this a was -2, this value right here would be -200, and our normal force would be less than the weight. So this is an example of an apparent weight problem. And anytime you see that phrase apparent weight, it just means normal force. And the math here is pretty simple, right? Up forces minus downward forces equals m times a, and we just plug in our values. The trick is just to remember, just because the person is not doing anything, he's standing in an elevator, there is a weight and a normal force, but the elevator is accelerating. So this was how we do a normal force, an apparent weight problem. And you could have a couple other problems with similar type of setups. All right, the second piece that I want to look at for looking at normal forces is going to be involved in inclined plane. So here we have our inclined plane. And the idea is if we put a block on this inclined plane and we raise this incline up, eventually the object will begin to slide, right? And so this is the next type of problem we want to look at. How do we consider this type of motion if we have a block on an inclined plane? And we're actually going to look at this in two different ways. First, we're going to consider this, what if there was no friction at all? And of course, if there was no friction at all on this inclined plane, no matter what, this box would be sliding down, or the block of wood would be sliding down, guaranteed, if there was no friction at all. And then we'll look at it again, what happens if there is friction, and how does that change our equation? How does that change our setup just a little bit? There is a little bit of a trick to this type of problem. And the main trick involves in how we look at it. So what are our forces here? And we'll draw it on the paper in just a minute. Hopefully you should see, we of course have a normal force, and that normal force is directed straight down. So the weight is directed straight down, not at an angle, right? Directed straight down. But the normal force, instead of it being directed straight up, is always perpendicular to the inclined plane. So where our normal force might be straight down, the weight might be straight down, excuse me, the normal force is actually at an angle. So we cannot simply add and combine the weight and the normal force because they're not parallel with each other. So what do we do? Well, the easiest thing to do, there's a couple ways to look at it, but by far the easiest way to do it is actually to change our coordinate system. Instead of calling X direction left and right, and the Y direction straight up and straight down, we're going to shift our coordinate system just a little bit. And we're going to call our horizontal axis parallel with the inclined plane. And we're going to call our vertical axis perpendicular to the inclined plane. And that's going to make our math much, much easier when we solve it. So I'll give you an example of what that looks like. Here we have a box, and we'll just give it a value. Let's say it's a 50-kilogram box. And let's say it has an angle on a 30-degree inclined plane. Well, what forces are acting on this object? If we assume there is no friction acting on this object, the problem's relatively straightforward. We have a weight that pulls from the center of the mass straight down. And we have a normal force, that's the surface, pushing up perpendicularly on the object. So here are our two forces. And if we do not have friction, these are the only two forces. So how do we resolve these vectors together? What angles do we have? The only angle we're given is the angle of this incline. Well, what we're going to do is a little bit of geometry. And what we're going to do is actually think about this weight. And instead of directing this weight straight down, we're actually going to change a little bit how we are considering that value, that force. And instead of the weight directing straight down, we're going to consider two components of that weight. A component of this weight that is perpendicular to the inclined plane, what I'm going to call weight perpendicular, and a component of this weight that is pulling it down the inclined plane, what we're going to call weight parallel. And so now we have a much easier problem where we can have our x-axis being directed here. And if you don't want to call it the x-axis, you could just call it the parallel axis, parallel to the surface. And our y-axis, or our perpendicular axis, being right here, where now normal and weight perpendicular are combined together with each other. Great. Well, that simplifies the problem down a little bit, but how do I find weight parallel and weight perpendicular? Well, if we look at geometry a little bit, you should be able to see if this is a 30-degree angle, we know what this angle is right here, right? This is a right triangle. So if this is 30 degrees, this angle must be 60, 30, 60, 90, right? And if this is 60 degrees, remember this forms a right triangle right here, or right angle, excuse me. So that means that this angle must also be 30 degrees. So this angle right here will always be the same as the angle of the incline. So we have a weight perpendicular pulling it down here, a weight parallel in this way. So, and this might be something that's worth memorizing. If you're not sure how to break this down or the math of it, if you at least remember that weight perpendicular, so the perpendicular component of the weight, that's going to be the component of the weight that's pulling it into the inclined plane. The way you will calculate that is mg, so the weight, and this is the adjacent side to the angle. So adjacent always uses cosine. Mg cosine theta. The weight parallel is always going to be equal to what? Mg, and this parallel is the opposite side to that angle, so we'll use sine theta. And let's think about this a little bit conceptually. If our angle was 0, what does that mean? Well, if we have an angle of 0, that means it's just a flat, there's no incline at all, right? It's just a flat ground, just a table. What's cosine of 0? Cosine of 0 is 1. So if we have a flat level ground, all of our weight is perpendicular, and sine of 0 is 0. So none of our weight is parallel, meaning if this was the object right here on a 0-degree incline, all of its weight is perpendicular, and none of its weight is pulling it down the inclined plane. As the angle increases, cosine theta is going to get smaller, meaning less and less of the weight will pull it into the surface. And sine theta is going to get bigger, meaning more and more of the weight will pull it down the inclined plane. If we end up having a 90-degree angle, we have an object on the 90-degree angle, weight is still straight down. Well, cosine of 90 degrees is 0. So none of its weight is perpendicular to the surface. None of its weight is pulling it into the incline. Sine of 90 is 1. So all of its weight is now parallel to the surface. But overall, this is our main setup. So what do? Well, let's draw our free body diagram. Weight is directed straight down. The normal force for this problem is going to be at an incline, or at an angle perpendicular to the incline. And then from here, we can set up our chart, right? So we only have two forces, the normal force and the weight. In this case, I'm going to think of x as the parallel direction and y as the perpendicular direction. The normal force is in the positive perpendicular direction or in the positive y. Essentially, we're looking at our problem as if this was the x-axis and this is the y-axis. So normal force would be up, positive y, or positive perpendicular. So I'm just going to write in here. And what about the weight? We have weight pulling it down the inclined plane. So down the inclined plane for the x direction is weight parallel. So mg sine theta. And depending on if we want to call up the incline or down the incline positive or negative, it's kind of up to you. For me, I usually consider on these type of problems, whichever way the object is moving is the positive direction, just because it makes the math a little bit easier. You know, I could just have easily drawn this problem like this with an incline here. If it's bothering you that this is pulling to the left instead of the right, your inclined plane could just be like this instead, right? And it'd be the same problem. So I'll just call it positive because I like calling down my, whichever way it's moving, the positive direction. I just find that makes it a little easier for me. But if you want to call it negative and set down the inclined plane as negative, that's fine as well. And then the perpendicular would be weight perpendicular, which is mg cosine theta. This one we do definitely want to call negative because it is opposite of the normal force. So negative mg cosine theta for the weight. So what are my two equations? We have a parallel equation, which again, my net force in the x direction would be mg sine theta equals what? Is it accelerating in the x? You bet. So it equals m times a. And what we actually find is the mass here ends up canceling out of this equation. So without friction, the acceleration is just gravity times sine of the angle. Simplifies down quite a bit. For the y direction, it's pretty similar. For the y direction, remember, F equals ma is our big equation, so we get that F by adding up the components. Normal minus mg cosine theta equals m times a, but it is not accelerating in the vertical direction. It's not suddenly lifting off the inclined plane, right? Or falling into it. So we could just say it equals 0. And so we could say our normal is equal to mg cosine theta. And if we were asked for that value, maybe we plug in 50 for mass, g is 9.8 or 9.81, whatever they want you to use. This angle might be 30 degrees, and we could find that problem. So pretty simple here. Let's do it again, but this time we're going to add in friction. And I think what you'll find is something a little interesting reveals itself when we add in friction. Of course, we can get more complicated problems. What happens if it's being pulled up the incline, or if there's another force at play, right? When we can continue to add on these forces with whatever we want to. But let's do it 100 kilograms. Let's call it a 30-degree angle. I'll have it set this way, so down the incline now feels more naturally to be a positive direction. But this time, let's say there is friction, and let's pretend the coefficient of friction is 0.2. All right, so we have a coefficient of friction. This will be our coefficient of maybe static friction or something along the lines of that. Maybe we want to find what's the acceleration, right? How much is it accelerating? Actually, let's say we don't know what the angle is. Let's say we do this problem, because this is kind of a more fun problem, right? If we did that, we could pretty much find the acceleration, not too bad. But let's say we have a maximum static coefficient of 0.2. This is our maximum static coefficient of friction. And we wanted to find what is the angle before this object is going to begin to slide down the inclined plane. And this is almost how we did our lab the other day. What is that angle that is going to be that maximum angle before it begins to slide, right? The steeper and steeper it gets, eventually it's going to slide down. What would that angle be? How can we predict it? How can we solve it? And if there's no other forces on it other than friction, it actually maths out to be pretty interesting. So let's draw our free body diagram. We have, of course, weight directed straight down. Our normal force is going to be up and to the right at an angle. So weight is straight down here. Normal force is perpendicular to the surface. And then friction is opposing motion. And so this box is trying to slide down the incline. So friction will be directed up the incline. So here's our frictional force. So this is our free body diagram. But with this weight, it's a lot easier if we break it down into components, right? So that's what we'll want to do in our chart. In a true free body diagram, we do not draw components on a free body diagram. We only draw the actual forces. Although I know sometimes after I've drawn it, I find it to be helpful to kind of like maybe sketch in, oh, well, instead of weight, we're going to have a perpendicular weight and a parallel weight. But in a true free body diagram, we don't want to do that. If it's an accurate and good free body diagram, no components are labeled. So let's go to our chart. X and Y direction. Remember X, we're going to call this the parallel direction. What forces are pulling it in this direction for our X, and Y is going to be our perpendicular direction. And we have three forces. We have normal force, we have friction, and we have weight. So our normal force is right here. It is directed upward. Remember, if we consider this as our X and Y, the normal force is in the positive Y or positive perpendicular side. So we're going to write normal force right there. Friction is opposing motion. I'm going to call down the incline the positive direction. So friction is up the incline. So I'm going to say that is in the negative parallel equation. And instead of just writing F for friction, I'm going to go ahead and write in my equation. And we are trying to find the maximum static friction. Remember, static friction is variable. So it's going to get bigger and bigger and bigger as this incline increases until it reaches its threshold. And once it reaches that threshold where we're at maximum static friction, any bigger than that, it's going to move. And the friction will switch to kinetic. So our equation for friction, though, equation for maximum static friction is mu times the normal force. That is our formula for friction. And the reason we're having it as negative is because it's up the incline and I'm calling down positive. For weight, this is where we'll use our components. Remember, for our weight, we are splitting it up into weight perpendicular and weight parallel, with this angle being the angle of the inclined plane. So the weight perpendicular is always going to be the adjacent side. You want to make sure you are able to break its weight down into components on an inclined plane. So if we wanted to find weight perpendicular first, weight perpendicular is the adjacent side. So that is going to be mg cosine, or it's down. So I'll call it negative mg cosine theta. And then weight parallel is pulling it down the inclined plane. So that is the opposite side. And we call this the positive direction. So we'll call it mg sine theta. Definitely want to make sure we remember how to calculate out these into our components. So now we set up our net force equation, right? We have one in the X and one in the Y. F equals ma is the big idea. So for the X direction, we just add up the columns. I'm going to actually do mg sine minus mu times normal, just because that looks nicer than the other way around. So mg sine theta minus the coefficient of friction times normal force equals what? It is accelerating in the X direction. No, it's not. We were, for this problem specifically, we are trying to find the maximum angle before it begins to slide. If the problem had given you an angle and it was accelerating down the incline, then we would say equals m times a, and we would just solve for maybe a if we're looking for. But for this specific problem we're looking at, the question I asked was, what is the angle that we're going to reach before it begins to slide? What is that maximum angle it's going to be before it begins to move? And so before it begins to move means it's not accelerating. So no acceleration in here. We're looking for the maximum angle where it's able to stay at rest. So we will say equals 0 for this problem. And again, like I said, this problem could have lots of variances. Maybe there's something pulling it up or pushing it down. But for now, we're looking at a box at the maximum angle before it begins to slide down. So mg sine theta, that is the parallel component of the weight that's pulling it down the incline, minus friction, minus mu times normal. And since we're looking at it before it begins to slide, equals 0. For the Y direction, same thing. Add up the column, normal, minus mg cosine, equals, and again, it's not accelerating in the vertical direction either, so equals 0. I can rewrite both of these equations just a little bit. Mg sine theta equals mu times normal. Normal equals mg cosine theta. I've got a mass and I've got g, but I don't know what normal force is. I do know mu and I don't know the angle. So what do we do here? Well, when we have two equations, this is where friction really comes into a play. We see that these two formulas have normal force in both of the equations. So what I'm going to do is I'm going to take this formula and rewrite it, but plug in my second equation's expression for normal force. So I'm going to write mg sine theta equals mu times, not normal, right? Mg sine theta equals mu times normal, but instead of writing normal, normal equals what? Mg cosine. And you might be able to start to see why I find this problem interesting. Let's look at this equation. We can simplify it more than you may think. M and M are going to cancel out. The mass cancels out. What about G, the gravity? Also going to cancel out. So we get sine theta equals mu times cosine theta. Well, we were looking for the unknown angle, so let's move the angle all to one side. Sine theta over cosine theta equals mu. And maybe you remember, maybe not, but sine over cosine is opposite over hypotenuse divided by adjacent over hypotenuse. That simplifies down to just what? Opposite over adjacent. Sine over cosine is one of our identities. That's just tangent of the angle. So this whole big problem really simplifies down to just the coefficient of friction is equal to the tangent of the angle. And if I wanted to find what that angle was, we could say the angle is the inverse tangent of mu. And we could find what that maximum angle ends up being. And the inverse tangent, I don't have my calculator handy, but the inverse tangent of 0.2 would give us whatever that answer is. So an interesting question. And I'll zoom out here a little bit if you want to look at it as a big picture. If I can get this, there we go. So to recap, with friction, what do we have? Well, we have friction, normal force, and weight. We took those three forces and broke them down into their components. Normal force was all perpendicular. Friction was in the negative x direction, and weight had its components that we separated using geometry. We then set up our net force equations. mg sine theta minus mu times normal, so just adding up the x's, equals 0, because we were trying to find the maximum angle before it begins to slide, so it was not accelerating. And then for the y, same thing, normal minus mg cosine. We then had two expressions, two equations that we did a little bit of algebra to, and we combined those together to get this expression. The weights end up actually canceling out. Solving for the angle ends up giving us tangent of theta equals mu. So this problem only works if there's no other forces and we're looking for the maximum angle, right? If it was accelerating, this one wouldn't equal 0, it'd equal m times a. If we have a specific angle, it might change the problem a little bit. There's lots of variances in all of these force problems, but if you know how to set them up and how to solve them, you should be able to have the tools to tackle just about any type of problem that you might see. All right. So hopefully that was a help for y'all on those type of problems. If you would now take a moment to go into Canvas and find the Learning Catalytics module that is labeled Rigid Forces and Normal Forces. It'll be in the Canvas lecture course, the UT version under assignments. It is just a Learning Catalytics module, but it's a Canvas version, so you get unlimited attempts on them. Go through that with each other, talk about it with the people next to you, and see if you can figure out the answers to those questions. We'll take a look at them a little bit when I come back, but also have some time to look at questions. All right. After you've done that, there will be a second video on something called an Atwood's machine. So make sure you watch the second video after you've done the Learning Catalytics.